Hello, we are Team 1, and for our project, we did long-distance autonomous parking lot navigation. The problem we wished to solve was to safely navigate through a parking lot while encountering as few obstacles as possible, while following driving regulations and maintaining parking conventions like when to cross the lot. We believe that for parking lot scenarios, with the knowledge of the environment through sensor data and map data, we can create a path planner with intuitive behaviors, such as following all the previously mentioned behaviors.
For our implementation, we have controller, decision, and path planning, and our main focus in this project is the path planning part. In order to validate our algorithm, we created our own environment in the gazebo, and we extract information from the world file to create a map shown on the right. The gray portion is the road, and the black squares are the obstacles, and we redefine the free spaces as the places in the parking road, but not in the obstacles. For the path planning algorithm, the first thing comes to mind is the PRM. We basically create a graph and get free spaces and obstacles from the world file, and we do sampling and add those samples to the graph. And for each samples, we check for possible neighbors to see if there's a valid edge between them, and then we run the extra to find shortest path. For the video demonstration, we can see here is a instance of running PRM. And the good thing about PRM is that it has many samples so that you can get different paths. But the bad thing is that it does not follow the driving regulation, the rule of the road. And also sometimes the algorithm can get very unlucky so that there's no path to find or inefficient paths.
So this is why we created our own method, which we named the grid method. The first thing we did for this was we sampled the map in a grid pattern right here. Then for any samples within an obstacle, we sampled around that obstacle. Then we drew directed edges between these some of the paths. So we have a distinction between left and right lanes. So the directed parts follow the rules of the road. Then we drew undirected edges between these nodes so that the car would be able to do U-turns or if it needs to. And we connected the rest of the roads together, and we just ran Dijkstra's to find the shortest path from the start and end using this method. So one disadvantage of using this method was that some of the turns are super sharp. For example, here it's a 90-degree turn for this instance, which isn't great, but this also shows like the car is able to follow all the rules of the road by maintaining its course on the right path before driving to its destination. And the consistency of our grid method was much better than PRM since it's not randomly sampled.
Okay, now let's talk about some numbers. We compared the grid method against the PRM in our static environment. We had 5 different queries and we performed 200 trials on each query. The PRM success rate was 91 to 98%, so that means it didn't find a path 2 to 9% of the time. On the other hand, the grid method always found a path. It was just a question of whether or not that path was good. We compared other quantitative stats as well, including runtime and roadmap size measured in edges and vertices. So in this presentation, we'll only cover 2 of our queries. The remaining are found in our supplemental material. For this query, we start in the middle and our goal is on the bottom right. It is a fairly simple query and the PRM success rate was approximately 96.5% of the time. So what we're showing here are 4 histograms. The pink represents the grid method's path length, runtime, graph size, and the gray represents the PRM's path length, runtime, and graph size. We see in this first chart here that our method performs as well as the PRMs in terms of path length. However, as we see in the following 3 charts, we are significantly faster and our graph size measured in both edges and vertices is significantly smaller. Also, we noticed that the PRM's runtime and graph size is significantly more variable than ours. We see that we have 1 histogram column here, whereas the runtime is sort of all over the place, the same with the graph sizes. We then tried on a harder query. This one has a start at the top and the goal down here. There are two possible ways to get through this environment. The first one being the long path through all the obstacles as shown in the top row. And the second one is a short way cutting corners through each of the other cars. And similarly, we see a bimodal distribution here. Our path length is comparable to that of PRM, and we see a runtime and graph size that is significantly smaller and less variable than PRMs. So in summary, if you remember nothing else from this presentation, remember that the grid method follows the rules of the road. The one we created stays on the right side of the road. It has consistent behavior and comparable path length to PRM. It is also more time and space efficient than the PRM method. Thank you for your time.
One of the reasons why we took this course was we wanted an introduction into autonomous driving and some of the technology behind it before deciding on whether or not we want to be able to use this technology ourselves in our cars.
And we are having a wonderful learning experience in this class. The various topics, including perception control filtering, localization, and path planning, are very useful for us in pursuing our future study. And the knowledge of path planning also benefits us for our project.
The best part of this class was most definitely getting a hands-on experience in the step-by-step development of autonomous systems through the MP and the project. We had a lot of fun together, the three of us, and this was an absolutely wonderful class to take the last semester before we graduate.
Yep. Thank you.
Thank you.
Thank you.